ultimately trying to say I can only, if I have a pattern like this in which my ith bit is 1, I minus 1th bit is 1, and the remaining bit, which means I minus 2th bit to the 0th bit is actually 0, only then I can make my this ith bit changed and make it to a 0. Again, it's a word as change. Now I have to return the minimum number of operations to transform n to 0. We will have a quick check on the examples, and then we will just start off very imaginary and intuitively on how to break down. Again, it's a very hard, so we cannot just directly say that okay, random number, because you can end up in multiple possibilities. Because in these cases what end up happening is you end up happening with a multiple cases, multiple possibilities, but we will not go in that way. We will see that how we will go. So we will have the number n as 3. We can represent the number as binary form, which is 1 1. Now first option or second option, which option to choose? Again, in the example itself, let's think which option we'll choose. If I try to choose the option number 1, then I will replace this 1 1 to a 1 0, right? But then to replace this, I ultimately also need to make a 1 again. So it's a flow point. So what I will do is I will first, and I want minimum number of operations. So what I'll do, I'll firstly make this a 0 by using operation 2. Okay, this has become a 0, and ultimately by using operation 1, I can make the last bit as 0. So operations required 2. For example, in the question number 6, again I have 1 1 0. Again, option 2, I can directly see it is happening, so I'll just directly use option 2 to actually make this bit as 0. Okay, it has become a 0. Now the number remaining is 1 0. Again, for 1 0, I want to apply any of the operations. Operation 2 I cannot see is being applied, so what I'll do is I'll for sure apply operation 1, because operation 2 I cannot see being applied here. So I'll have to apply operation 2. I'll apply the operation 2, and it will become a 1 1. Now with 1 1, now I can apply the operation 2. So I applied operation 1 and make it as a 1 1. Now I'll apply operation 2 and make it as a 0 1, and then I'll apply operation 1, and then I'll ultimately become 0 0. So that's the example, which is kind of okay. We know that okay, when we can apply operation, we will apply that operation, else we will not, but that is not much useful. So what we will do is we will start off with an imaginary number. Let's imagine any number, like in this case I just took any imaginary number. Again, you will see that in mid you have a 1. It is not it is neither directly you can apply option 1, neither you can apply directly option 2. So it's both ways, no one can be applied here. So that's the reason we just took it. But looking on back to your 2 transformations, which you can do is, the first transformation just said that you can only change the last bit. So the first transformation can only change the last bit. I cannot change the other bits because of the first transformation, but because of the second transformation I can change any bit. So this is for any other bit I should be changing. Now you will say any other bit, but what if it is not even transformable? We will go into it, but you will see that to change any other bit I will have to apply operation 2. So why not, let's start with seeing that how operation 2 we can leverage, because to apply transformation on last bit it is operation 1 for sure, but to apply operation on any other bit we will for sure use operation 2. So let's leverage operation 2 and see how we can actually use operation 2 itself. So for sure operation 2 just says one thing, that again how we reached it, because we can only leverage operation 2. So let's take operation 2 in our hands and see that how we can leverage operation 2 to reach to our final answer. So operation 2 says that if you have something like ith bit, I minus 1th bit, both are set and all the bits are 0, then you will need just one operation to transform this number to a 0 1 0 0, which means you will just make this number as a 0. That's great, but ultimately your aim was something else, right? Your aim ultimately was transforming this number 1 1 0 0 to a final 0 0 0 0. Again, please remember the count, right? Because it will be helpful for you to actually imagine in the binary form. Now, my ultimate aim was to make a 0 0 0 0, but I have not reached that. I just have used one operation. What about this number itself? I will ultimately have to reach to a 0 0 0 0, right? So manually, again, it's a problem where you have to figure out the case. So manually check how we can reach to a 0 0 0 0. Again, it will not be a case where you will, okay, my entire hard work has gone to waste. It will not happen. It will be very useful. Now, what we will do is we will try to manually reach, because see, this portion has already become a 0. Now my main aim is to make 1 0 0 as a 0 0 0. So I'll manually I'll manually write down and transform this of 1 0 0 to a 0. 1 0 0. Apply operation 1, make it as a 1 0 1. Okay, now apply operation 2 on this bit, because you see this is a 1, and I can change this bit and make it a, I use operation 2 and transform this to a 1. Now I'll use operation 1 and transform this to a 0. Again I'll use operation again I use operation 2 and transform this bit to a 0. So I got this bit as a 0. Again I need to apply some operation, but I cannot see anything, so I'll apply operation 1. I apply operation 1 and transform this bit to a 1. That's good. Now I'll simply apply operation 2 on this bit and transform this to a 0. Lastly I'll apply operation 1 and transform this bit to a 0. So you will see that you obtained, again right now I just showed you. Again, this will be very useful. I will copy paste the same stuff later on also for further observations, but you saw that how we flowed in. But now you'll see that, okay, you just got this transformation. Now if I just ask you, you reached from 1 0 0 to 0 0 0, right? Was it possible to reach from 0 0 0 to 1 0 0? Like, just look at it, just look at the images. Like, I just have gone from 1 0 0 to 0 0 0. The same way I can go backwards. I can just replace this again. That's the reason in the beginning I said it's a change, right? So I can just change this bit, make it a 1. I can change this bit, make it a 1. Apply operation 1, make it a 1. Apply operation 2, make it a 1. Again, apply operation 1, make it a 0. So there's a change I was doing. So for sure, if I can go forward, I can also go backwards. It ultimately means from 0 0 0, I can also go to a 1 0 0. But Aryan, why is this helpful? You will see when we will go one step above. But yeah, right now, so you have seen that how we reached a conclusion that for sure if I can go from A to B, then with the above operation of change I can go from B to A also. So that is for sure, and you will see that operation required, let's say here are X, so here also operation required will be X itself, because it's just a backward arrow which I have just supplied same. Now why was this useful? This was useful because here we took as a 1 1 0 0 and we transformed it to a 1 0 0 and then transformed that number to a 0 0 0 ultimately. So you will see that 0 0 0 0 ultimately. You will see that here I use X operations. So if I just go one step above this, so if I had a 1 0 0 0 and then I can transform this. I know that if I have something as 1 0 0 and then if I want to transform it to a 0 0 0, then I need X operations. To transform 1 0 0 to 0 0 0, I need X operations. To transform 0 0 0 to 1 0 0, I need again X operations. So I know if I just go one step above it, then I will have 1 0 0 0. So I know to transform 0 0 0 to 1 0 0, I need X operations, because it is same. Don't need to transform it. I need X operations. And for sure, to transform this part from, I'll use simple operation 1, which is just one operation, so that's good. And to transform my 1 0 0 to 0 0 0, I again need X operations. So you saw one thing, that how ultimately you were able to, if you have a bigger picture, you were able to reduce to a smaller picture just by using this reverse pattern concept. That if you had your ith bit as set, then you were able to bring it down to I minus 1, and then you were able to bring it down to 0 0 0. So ultimately the same thing I showed here, that if your ith bit is set, ith bit, I'm not saying what about the other bits, but right now I consider an example where just the ith bit is set and rest all bits are 0, then you can just use X operations to reach to a place where actually you transform that number to a pattern which can be transformed using operation 2, which means you have some big number where you imagined it as 1 0 0 0, which means ith bit is set and remaining all the bits are 0. You transform using X operations to a number which can then be transformed using operation 2 in one step. That's the reason I just went one step above of it, so as from a number I can transform using some operations. I want a number above it so that I can transform it to operation 2 Now, Aryan, how you thought of it? Ultimately, how I thought of it was because here you have this imaginary number. Ultimately, you have to transform this imaginary number to your number right here, so that you can just use apply, so that you can just use operation 2 and apply operation 2 in it, right? And then when I apply operation 2, I reach to a number like this. And then ultimately I also saw if I have a number like this, I can transform this using x operations to a number as 0, 0, 0. So why not I can just say that I have something as 1, 0, 0, 0. So I can just say 0, 0, 0 to 1, 0, 0 and 1, 0, 0 to 0, 0, 0. Same x operations will be applied here. So that is one thing which is kind of that, okay, how will I think of it? But still, it is with writing and finding a pattern out. Okay, that is one thing which clicked our mind. So now the hard part is just this part being clicked. That's all. It's the hard part. That's the reason why this question is becoming like why this question is hard. Cool. Now, when we have figured out a pattern that this is happening, so we can just say that f of I is nothing but, if I have ith bit as set, then I can use x operations, reach to a number. I use 1 operations to reach to 1, 0, 0, and then again I can use x operations to reach to a final 0, 0, 0. So I'll write the same thing as f of I equal to 2 into this x, you will see it is nothing but 2 into f of I minus 1, I'll write, and then plus 1 for this operation number 2. Why? And you will see that you initially had ith bit, and then you were at I minus 1th bit. And the transformation also itself was on the I minus 1th bit here itself. So you will see that x is nothing but I minus 1th bit. It is I minus 1th bit, and that I minus 1th bit as set, and remaining all the bits as 0, and then we did transformation and that we counted as an x. So you can easily see the formula which you have made right now is f of x equals to 2 into f of I minus 1 plus 1. Now where I says ith bit is set, I minus 1 says I minus 1th bit is set. So this is one thing which you have got. Now why was this useful? We will see, but it is kind of that we again further broke down the problem to just say that if I have 1 and all zeros, like earlier I had only one pattern. Earlier I had a pattern, okay, all zeros, and earlier I had a pattern that whatsoever and last bit either it is a 0 or a 1. I had a pattern 1. Now next I had a pattern where I have 1 1 and then all zeros, then I have a pattern 2 which is observation 2 or the transformation 2. Now I have one more pattern with me, that if I have 1 and remaining all zeros, then also I know that the operations required are what? Here, let's say here it is x, here it is x, so I also know this fact. So now for this operations required were 1, for this x. I just figured out one more formula for me out of the 2 formulas which were given for me. Now coming on back, what was this formula? Simply, if you had a 1, you know it's just one operation by using operation number 1. If you had 1 0 0, then for sure it's a f of 1, right, which is 2 into f of 0 plus 1. Simple, like using the previous value, so it will be 3. So you know for this value it's a 3 operations required. For this 1 0 0, it's required will be operations which are 7. So you know that with this kind of 1 into something which is all zeros, now like the number you can easily figure out. So to convert that to a 0, you know that now you will need x operations, and that x you can easily find out by using this simple recursive formula. Now coming on back, that was not the question for us. My main question was any imaginary number, convert that number to a x, like convert that number to a 0 0 0, right? Now the same thing which I wrote above, I'll write that same thing down up below. That's the reason I said everything you dry run or basically check out while formulating or figuring out a formula that will be useful for us. So you saw that you transformed 1 0 0 to a 0 0 0. You saw what happened in between. When you transformed your 1 0 0 to a 0 0 0, you encountered every number which is of 3 bits. So you saw you counted 0, 1, 2, 3, 4, 5, 6 and 7. So while transforming, you encountered every number. So I'll just say the same thing, that this is the parent of any number in between. What I mean by that is, if I have any imaginary number of, let's say, 1 2 3 4 5, I have even any imaginary number of 5 bits. So for sure, when I will be doing a transformation from 1, which means 1 at this bit let's name it as a 4th bit. So 1 at the 4th bit, so they basically, the number of bits are 5, so this, the 4, like the leftmost bit will be the 4th bit, and the left and so and the rightmost will be the 0th bit. So I'm just saying that for the leftmost bit, that is the parent of everyone, while I would be transforming from that 1 0 0 0 0, while I will be transforming this number to a 0 0 0, for sure this number would be coming in between. And this is how we prove this by using the above diagram which we saw. So because we know that every number in between will for sure come while transforming to a 0 0 0. So I know that, okay, to transform this 1 0 0 0 0, which means if I have 5 bits and the 4th bit is set, I know that for sure the operations required will be f of 4. I represented my f of 4 with this XOR of 4, so that you don't get confused. It's just a power, right? So f of 4, but ultimately the answer is f of 4. So I represented, okay, we know this fact that to convert this 1 0 0 0, I need f of 4 as my, or basically this XOR or power of 4. Let's name it as f of 4. So I need f of 4. I know this value for sure, and I wanted to find from this 1 1 0 1 0 imaginary number to my 0 0 0 what should be operation required, that is x. That's unknown for me. So ultimately, if it's unknown, I know this fact, can I just find out the number of operations required to transform this 1 0 1 0 0 0 to this 1 1 0 1 0? Can I know this fact? Yeah, that is what we can get to know. How? Simple. Can we just see what is not there, which means you see that this part, this one is same, this one is same. Okay, this part is what I need to convert, which means I need to convert this 1 0 1 0 to 0 0 0 0 again. Although I am saying I need to convert this 0 0 0 0 to actually a 1 0 1 0, but we saw if I can convert A to B in X operation, I can convert B to A also in X operation. So that also is being used again. So I know one thing, that I will convert this 1 0 1 0 to a 0 0 0 0. Again the same concept. I'll just find out the parent. Parent is simply, if I have 4 bits, the third bit, which is the leftmost bit, it is set. I'll simply say he is the parent, and from this bit to the 0 0 0 operations required are f of 3. F of 3 operations are required, that we for sure know previously. We just simply pre-computed. Ultimately my aim was to reach from 1 0 1 0 this to a 0 0 0 operations required are y, which is still unknown. So I'll just simply do, I can simply find out this value, which means from 1 0 0 0 to 1 0 1 0. Again I just say how to figure out. Simple. It is same, it is same, it is same, it is same. I need to convert my 0 0 to a 1 0. Again, convert your 1 0 to a 0 0. Now you will see it's a simple parent only, so that will require f of, let's say the operation required as z. Now this z is nothing but f of 1, because it is at the first bit, and that is a 1 kind of like 1 and all zeros kind of formula. So I can simply apply my f of that formula itself, which I earlier found out. So I just simply say that for this z, my answer is f of 1. Right, now for this y, answer will be f of 3 minus f of 1, because you saw f of 1 was the answer for this, which is the z. Z was the answer, right? And z is f of 1. So I know that y is f of 3 minus z, which is actually f of 3 minus f of 1. It is y. Now again, I'll just simply replace this y. I know x is f of 4 minus y, and y is f of 3 minus f of 2. And the same thing I will write, that it will be f of 4 minus f of 3 plus f of 1. Now if I just simply know that, okay, it is my final answer, f was nothing but what we find out, 1 1 2 4 0 1 2 3 4. It is nothing but, like, for this value, f of 4 is nothing but representing for this value, for this particular value, what was the value, what is the f value for this. Now this will say it is 0 1 2 3, it will say I am 0, it will say I am 0 1. So I know for these corresponding values, I can simply pre-compute the value in the beginning, and I know that for odd places, because my random number, where my random number found, my imaginary number was 1 1 0 1 0. I write the same number here, 1 1 0 1 0. You will see 0 first, second, third, fourth bit. For the first bit I am doing a plus sign, for the next I am doing a minus, for the next I am doing a plus. Simply keep on alternating your bits and keep on adding a plus sign for the first bit, for the next minus, for the next plus, and keep on going. And you know that you have your n as less than equal to 1e9, which is nothing but 31 bits, sorry 32 bits in total, sorry 31 bits in total. So thus you can simply find your answer. That is how. Again, a quick recap on what we did. Again, that was entirely nothing we assumed, and that was entirely in the flow of the question. We saw, firstly, we figured out that we have an imaginary number. Now this imaginary number, we know that we have just two operations, last bit and the other operation, which will actually be impactful for other bits. So just to figure out for this imaginary number, we just went on and figured out that we can only use operation 2 as our main operation. Operation 2 is as our main operation. Now for that main operation of operation 2, we just went on and checked in that how operation 2 works. Operation 2 works as if I have a 1 1 0 0, then it will transform to a 0 1 0 0. Now when this is done, so ultimately my aim was to transform this transform this number 0 1 0 0 to a 0 0 0 0. So I just manually from my pen wrote the same thing down. Then while writing, I also realized that reverse is also a true for this. So with this I have got to know one thing in my mind, that the reverse is also true. But ultimately my main aim was to find out that how I can do it for my any imaginary number. So ultimately I thought of, let's maybe if we can able to figure out some relation. For that I went on to its parent. Now its parent can be any number which I can use and find a relation to in this entire sequence. So I went on to its parent. Its parent was 1 0 0 0. From this I can know that this portion is same, because I have figured out that the reverse is true. So I can just say if I have transformed my 1 0 0 to a 0 0 0, that's also the same as 1 0 0 to a 0 0 0, and I can just simply place a 1 here because it is the same bit, so that would not count as a transformation. So I know that if it requires x, it requires one operation 2, and then it requires also x. So with this I have found a relation for my simple concept when my ith bit is set and remaining all the bits are 0. I found a relation for this. Now this relation is a third operation which I can perform, but it's just that the cost will be now x for this, which I can simply find by using a recursive formula. Now when this portion is done, ultimately I went back onto my imaginary number and tried to transform this imaginary number to a 0 0 0 again. But while I was doing this by expanding my number, I figured out that as it is a parent and it will, while making my answer reach to 0, it will reach on to every number. So for sure, if the parent was a 1 0 0 0, while reaching to a 0 0 0, it will have a mid number in between. So for sure, if the operations required here are x, I can simply able to figure out this operation y, and this I can again go and went down, again go and went down, again go and went down. With this again coming back the values, a simple mathematics, and then we got the relation that it is nothing but odd even, which means plus minus by just simply going if the first bit add its f value, next bit subtract add f value, and so on and so forth. And with this your time is O of 31, because you will simply go on to 31 bits. Space is also O of 31, because for sure you will need f thing. So let's quickly code this up, that how we'll code it. Now as we saw that it can go to although it should not, but for simplicity let's take it as a long int. So what we will do is we'll firstly want to have a f value, but you know that f value can go up to 31 bits. It will entirely have 31 bits from 0 to 30. So I'll just say for the 0, the bit as set, right? You know, it's just operation number 1, which is this operation right here. So that is just one operation required. For the remaining other bits, which means from 1 to I is less than equal to 30 and I plus plus. Now if you just say that see 2 raised to the power 30 is actually around 1e9, so that will actually work for us. So that's the reason we just took it. Now again we just simply go on and say that f of I is nothing but 2 into f of I minus 1 plus 1. With this I have got the f value. Now ultimately my aim was to find the answer, so that I will simply do, again I'll go on from the very end, extreme end, right? I'll go on from the extreme end of my bit. So I know that I have 31 bits starting from 0. I'll go on to the last bit. I'll just check if this current bit is set. If this current bit is set, how we check it? We just make a mask saying one left shift I times, that is a mask, and I'll do a and with n. So this mask will become a 1000, like at the ith location. If that is something, if this is something, which means if this value is something and not 0, which means my ith bit was set. Only if my ith bit is set, I will actually have to apply operation. But here you saw that, okay, I need to maintain my odd even kind of count. So I'll just simply, as soon as I have got any bit set, I'll just check the count, and then I'll just have a quick check. If that count is odd, which means I'll just simply add that value in my answer. Add that f value in my answer. Else, if the count is even, I'll just subtract that f value in my answer. That is what my final formula looks like, right? So ultimately, I'll just simply return my answer, and with this, you will simply be able to solve it. Cool. And you will see the time is actually O of n, and space is also actually O of 31, and space also O of 31, because 31 here and 31 for the space. I hope that you guys got it, the entire intuition. That's the reason I spoke. It is very directional flow and also intuitive. Cool. Bye bye.